let's start. Okay. Just to give you a little bit brief agenda of what we are talking about. Of course, I will give to you a little brief presentation of me and the organizations I work with, and we will talk about our approach for the deep learning for post-earthquake safety evaluation of Masonry building. And especially we will see two methods that we developed. The first one that was already published and shared with the communities, and the second one that is actually under review, and also the upgrades that we are making on our approach. So just to start, who I am. I'm Giovanni Giacco, and I'm a PhD student at the University of Naples Federico II, based so in Italy, in south of Italy, Naples. And I started the PhD 3 years ago, so I'm at the end of this journey. And I had a master's degree in computer science in 2019, and I started the year after the PhD. I have a strong background in software engineer because I have more or less, actually, I think 12 years of experience in sector of information technology. So I started as a software engineer more or less 12 years ago. After that, after 3 years, maybe I switched on sides of artificial intelligence and generally data science. So very early in the sector, and after that, I continued with this passion and also with trying to improve my skills in this, and started the PhD 3 years ago. With this strong background that I have in software engineer, I'm also a CTO in a startup company based here in Naples. We will talk a little bit about the company that is also part of the Tema project, projects, and so I am just to tell you that I have a PhD. I'm working on a PhD in artificial intelligence applied in Earth observation, and of course, I think you know what it's about. So we are trying to use generally every kind of geospatial data, so pollution data, weather data, but generally every kind of remote sensing data. Especially, I work with satellite imagery, all kind of satellite imagery. Not a lot of SAR images, but especially optical images. My experience is more on optical ones. And the idea is, let me say, my experience, my skills are not focused on the creation of new, let me say, artificial intelligence, in general, machine learning methods new in the literature, but more focused on the creation of products based on artificial intelligence. And generally, I try to combine several approaches that does not use only machine learnings, but try to combine more traditional algorithms to create an end-to-end solution. And I think what we'll see today is a good example of what we can do, what products we can create when we combine artificial intelligence with other kind of expertise and product design. Just to give to you a brief overview of the groups in University of Naples where I work every day with. We are, as you can see, an heterogeneous and multidisciplinary groups because, of course, we are everyone focused on topics of artificial intelligence, but we are not only computer scientists. We have also lawyers, philosophers, because we focus also on the, for example, the parts of ethics of artificial intelligence. I am, of course, on the parts of the AI in the environment parts of the world, but in any case, we have, this is just some of the people that are parts of the group at the university, but at the moment we are more or less 25 people in the laboratory. We work on everything that is related on the pattern analysis in generally and intelligent computation of multimedia data generally. So we work a lot with video and images. And as I said to you, I am a CTO of the Latitude 40, where I'm working also at my PhD. Just to give to you a presentation of what we do in Latitude 40. We use generally, as I said, geospatial data, more or less satellite imagery. So the idea is that using satellite imagery, of course, you can go in the past because you have archive data. So our motto generally is see the past, monitoring the present, and design the future, because you can learn from the past and try to design the future with the data that you learn, with the information that you collected from the past. And just to show to you something that I worked with in the company, this is, for example, I don't know how many of you know, but this is a Sentinel-2 satellite imagery, an RGB, simple RGB Sentinel-2 satellite imagery that is a 10-meter spatial resolution. This means that each pixel that you see in the image is a box of 10 meters for 10 meters on the ground of our Earth. This is what the Sentinel-2 satellite imagery is, and this is what our model can see in the same image, in the same scene, because we developed an algorithm of super resolution that uses generative AI that can switch from this kind of view to this kind of view. So we can increase the spatial resolution of the image from 10 meters to 1 meter spatial resolution, just to give to you something that I worked in these 2 years. And we developed a lot of layers. Those are just some of the layers that we produce every day in Latitude 40. I won't go in the details of these layers because it's not the focus of this talk, but just to tell to you that we work a lot with the land cover classification, all the tasks related to land cover classification, but and especially to the monitoring of greenery infrastructure in the urban environment and the phenomenon of urban islands. So just to give to you a brief description of the actors that are parts of the project that I'm going to describe today, because this project is part of collaboration with the University of Naples Federico II, Latitude 40, and what we are trying to talk today is how we can use drone imageries, but not only drones images, but also images taken by technicians by smartphone, for example, to assisting the technicians in the compilation and in the compilation of the cards that they need to compile after a post-earthquake, after an earthquake that happened in part of the world. The needs here is that maybe you know, Italy, especially the center of Italy, is a part of the world where a lot of earthquake happens in the past years, because we are in a specific parts of the world where there are a lot of earthquakes. And of course, maybe you read in the last, I'm from Naples, and in the last months, there was a lot of earthquakes in maybe is 25 kilometers far from my site, because we have a part that is we are on the Vesuvio, the volcano, so there is a lot of movements of the lands. So in Italy, but also in all the world, there is the necessity to take care of this kind of stuff. And also, so we need to assist technicians because when you have to assess damages, you need to have a lot of people. So at the moment, because everything is manual, so just to give to you an overview of the post-earthquake damage assessment that happens actually in Italy. And but I think it's more or less everything in the world the same at the moment, the situation. At the moment, the safety, the damage assessment is made by very expert technicians that go where the earthquake happened in the days after the earthquakes, and this can happen also a lot of months before after the events, because everything needs to be in security. At the beginning, of course, you need to take care of people as not of buildings. So this is a very time-consuming process that is not at all compatible with a near real-time assessment, because you have few people with these high technical skills, and you can be so fast to have a initial overview of what happened in the city. Of course, what are the pros of this kind of process? Of course, it's the high accuracy, because everything is made by very experts. So there is a very high accuracy, and also the process is regulated by law, because in every country, also in Italy, you have everything is regulated in some standard flows that you need to follow from the happening of the events and is managed. So our solution is wants to focus, of course, on the near real-time parts of the problem, because you know, when something bad happens, the first need that you need is trying to figure out what happened and what is the severity of what happens, and you want to know this as soon as possible. So the idea is try to assess the idea is try to develop an analytical methodology that can try to assess these then can try to make this assessment in short time, in an automatic fashion, more or less automatic fashion, or at least with the intervention of few people that you need if you need to send technicians all around the cities. Of course, we are talking. We already know that we can't, but we will talk about that later. But we already know that when we develop something that is so challenging, let me say, because we have a process that at the moment is managed by very expert technicians, you already know that you lose something in the accuracy, let me say, of the solution. But this is something that we want to pay to have some near real-time assessment. The idea is that even having a near real-time assessment, you can organize you can plan what happens in the next days after the earthquake, because you can know at the beginning where there are more damages, where not, so you can organize your plans for the intervention, so for the mitigation after uh, um, the disaster happened, but also you can use data that we produced also to after the months after, also to try to help the reconstruction project plans, because of course you know everything about the buildings, about the area that have been affected from the earthquake, and also you can create a, a solution that can let me say, try to create an archive of data. So you have something that you can use later on when other kind of other similar earthquakes happens in the future, because of course they unfortunately will happen. So we proposed our approach. We shared with the community our approach. As I said at the beginning, I am a computer scientist. I'm not a civil engineer. I don't know anything. I know a little bit, thank you to this work, about structure of masonry buildings. But of course, my expertise is in artificial intelligence. So if you have question about specifically to the structural part of buildings, we can talk about that, but maybe you can send to me an email and I forward all your curiosity or to my colleague that are more expert about that. So we made this kind of stuff in collaboration with the Department of Structure for Engineering and Architecture, always inside the University of Naples, Federico II. And this is the first paper that we published. At the moment, we have a version 2 of the methodology that is under review, and is something we try to talk later on during the speech. This is an important slide for me, because for me it highlights a very important points when you need to talk, you need to deal with this kind of stuff about natural disaster management, etc. And this is that you can't manage everything. You can't build a product just using artificial intelligence, big data analytics, etc. But you need the expertise of people that have a very good expertise of the problem that you want to solve. This is the why we made this kind of a collaboration. And so I won't bother you with what is the process after an earthquake happens, but just to give you a brief description of let me just check if in the chat there is some question. Okay, no. Just to give you a brief description of what happens, at least in Italy, after an earthquake happens somewhere. Those are the name of these cards is EDES, and those kind of cards are very specific for Italy, but it's worth to note that they are very similar in every part of the world. There, of course, in Australia, in several countries, in several in USA, they are different from this, but they are very similar. Generally, technicians need to compile generally always the same information everywhere in the world. This is an important aspect because is just to tell to you that the approach that we developed is more or less applicable everywhere in the world. Of course, we'll talk later about that, but if you need to create a product end-to-end, so where you need to use the automatic evaluation with the compilation of something, you need to customize this country by country, of course. But just to, unfortunately, this is in Italian, so maybe you can't understand the language, but there are several sections, and generally there is a part where you need to compile how much bigger is the building, how many floors, etc. Very simple. But the most important parts of the cards is the section 4, that is this one, where the technicians needs to compile where the cracks in the buildings are and the kind of severity that is light, medium, hard. So you need to compile, okay, in the vertical parts of the buildings, I saw that there are 2 or 3 cracks and they are hard. I saw 1 medium, etc. So you need to compile the number and where you found this kind of cracks. This is something that you need to compile. Of course, we need attention about important points. This kind of assessment takes into account both the outside of buildings and the inner parts of the buildings. Of course, at the moment with our approach, we are just looking at the outside parts of the buildings. And of course, this can be a problem when you need to assess damages of buildings. This can be a problem because something could be not visible from outside. But as I said at the beginning to you, the idea is try to create a system that can create a fast assessment at the beginning. After that, you can plan to make an assessment more precise, more regulated, using technicians. Because you know, for example, that with our assessment, you know that in the S part of the city, there are more damages. So, okay, you plan to send 3 technicians in the west part of the city because it's more damaged, and just 1 in the S part of the city because it's less damaged. This is more or less the idea. But in any case, we are okay, and maybe I can describe to you later. Yeah, the idea is that I won't bother you, but because I'm not an expert too about that, about what are the mechanisms of structure of masonry structures. But generally, it's important to note that when you are dealing with the damage assessment by earthquakes of masonry buildings, generally for the physics that happens in the buildings, this is something that I learned during the project. Generally, you see some crack outside the buildings. Generally, it happens. You can see some crack outside the buildings. It's not just something that is inside your building. Okay? I am not, as I said, I'm a computer scientist, so I don't know anything of this slide. Let me be honest. It's something that I started to learn with the beginning of this project, but what I want to highlight with this slide is that you know, you have you need to take in account when you want to create an approach that needs to estimate damages by an earthquakes of masonry buildings. You need to know the physics of what happens. You can't just use artificial intelligence for everything, because you need to understand the whole approach that you want to create. And just to give it to you, sorry, just to give it to you the only points that you need to know. That is the one in this first sentence. At this, the building's response to seismic forces depends on structural connections and the rigidity of the floors. Sorry, just a moment.
Hello, everyone again. Giovanni, whenever you feel better, you can start.
Sorry, again, my voice. Sorry, I'm talking a lot. Okay. Can you see my screen?
Yes, we're working.
Okay, sorry for the interruption. The good news for me is I'm still alive. For you is that isn't bad, because you need to listen to me, I think, for other 30 minutes. So, but sorry for the interruption. Okay, so we stop at here. What I was talking about is that, of course, when you need to create an approach that use artificial intelligence, but need to create a model of something that is related to the physics of buildings. Of course, you need to know the physics, the physics behind that. So you can use just artificial intelligence trained, for example, on a data set of cracks, because for example, you want to just make a localization of the cracks in the buildings. What's noting in this moment that what I'm trying to explain to you during this talk is that we are not, maybe I hope it will be clear later with the next slides, is that we are not talking about some just crack detection by artificial intelligence algorithms on buildings. It's not just about that, but we are talking about a full product that can help the technicians. So it's not just about crack localization. As I said, you need to know the physics of masonry building structures. And we won't go in the details of that, because I'm not an expert about that, but just to give to you an overview of the physics, there are 12 types of common lesions types that you can have in a masonry buildings. We won't go in details about that, but what you need to know at this moment is that the difference in the lesion types is about where they are located in the structure of the buildings. So, for example, they are between two windows, or maybe they are are between two windows in the horizontal line, or in the vertical lines between the two openings of the buildings, of the facade of the buildings. They are in the angles of the buildings. So you have cracks, but they are not all equals. but their severity, the assessments of the damages of the buildings depends where the cracks is located on the buildings. This is the most important key points that you need to get at this moment. So, given that, we started to think about the approach that we could develop. And the idea is more or less related to three important phases that are of course, the identification of the cracks. Of course, you need to identify the cracks on the surface of the buildings, but it's not enough. You can't just identify cracks. But the second important step is that you need to locate the cracks. So you need to tell, okay, this crack is in this part of the buildings, this crack is in this other part of the buildings, because you need to go to the third step, that is the quantification of the cracks, but let me say the quantification of the damages. And you can do that only if you know all the cracks and where they are. So this is our approach. Let me say, this is our first version of our approach, because as I said at the beginning, we worked on a second version of the approach, and later on we'll understand why we made a second version of our approach. So let's just explain to you how our approach is. Of course, we start from the image acquisition. As I said to you, at the moment, our approach is agnostic about the kind of image that feed the system. They can be images taken from a camera, for example, a smartphone, but can be also images from drones. It's not matters. We just need an image of a building. Of course, we separate the process in two sub-steps that are the crack detection and the location and the building's zone labeling. Let me say, what we do is, let me say that this is the facade of a building. These are the doors in the buildings. These are windows in the buildings, okay? It's just something like that. Okay, what we do? We made the step of buildings zone labellings. Is let me say a simple approach. What we do, let me say if you have a slide, no? Okay. What we do is trying to understand where are the openings in the facade of the building. So we can, by means of artificial intelligence algorithms, understand that here there is an opening, here there is an opening, here there is an opening, etc. Okay? What we do, we make a labels. After that, we have a mask. So we have a mask of the buildings. We know where there are openings of the buildings. What we can do, we can create these, let me say, line, horizontal and vertical section. And we know that the section between, the vertical section between two openings, it is called spandrels because it's the technical name in masonry structures, etc. So as you can see, we have a S1, S2, S3, S4, and on the horizontal line, we have other kind of physical structure, let me say. So we can have the buildings, applied mask, know where are their openings, and we create at the end this, let me say, box on the surface of the buildings, okay? The other part, of course, is localized. And we make, by means of artificial intelligence, the segmentation of the openings in the buildings, and the creation of the box is not by means of artificial intelligence. We don't need that, of course, because we just need the mask, and we know that all the pixels in the horizontal part between few openings needs to be labeled with a P label, with S label if it's vertical. So it's just a matrix computation, very simple. After that, we make the detection of the crack. So maybe, let me say, we say that we have in the part P1 here one crack that is low in severity, and after that we can say that we have in P2 part 2 cracks with high severity, etc. What we construct is, let me say, this matrix that is very simple here, but maybe at the end we can see the whole approach, is a damage matrix assessment. This matrix can be used by technicians to make the assessment of the and compile the cards that I showed to you at the beginning. This is the first step. The second step is that you can create, and we created, a tool that from these cards, from this matrix, damage matrix assessment, can compile a section of the card. As I said at the beginning, we have this section 4 that is about how many cracks with which severity they have in the parts of the what parts of the building. So we can compile this kind of this section of the cards that is also the more important parts. Okay, so this is the approach that we created. And of course, you need to create something with artificial intelligence. So the problem here is anyway the data set, because generally you don't have the data set. So this could be a problem. What we did in this case, for this project, we started from scratch. So we had the chance to have a lot of images captured from smartphone and also from drones, but let me say that we had 70%, more or less 70% of images from drones, from smartphone cameras, and 30, just, yes, maybe less than 30% of images collected by drones. That were collected by the one of our structure in Italy that is that manage emergency. So they had the data and they shared with us all their images, real images after the earthquakes that we had in the center of Italy, maybe it's 4 years ago. And what we did, we started to label for each image several kind of stuffs. So, for example, we separated a global label, so something that you need to label on the whole scene, and something that you need to label on the single crack. Okay, so of course this was a manual approach, and I won't go in the detail of everything, but of course you need to check if where is the damage. Of course you need to define the kind of assessment, and but the most important is the right part of the slide, because of course maybe we can just switch to the image. Okay, maybe it's more clear. We have an interface. This is very important. We use an interface that is a web interface that is user friendly, because the labeling was made by people that are very expert in the sector of assessment of damages, but they are not tech savvy. They are not expert about artificial intelligence. So they need to have something that is very user friendly for them. And also this is also a very important point. We also made at the beginning a training for people to understand how they need to label the images. Okay, and so maybe you can see here an example. What the user need to do is define what all the openings in the buildings. They need to define the area of the cracks. They need to design the line along the crack, and they need to design also. This was not necessary at the end, but also the area of the facade of the buildings. So a lot of stuffs. And also for each crack that the user detect in the image, it needs to define the kind of severity that is low, moderate, or high. And we defined a clear specification for low, moderate, and high that is about the shadows and the millimeters that you can see or imagine, let me say, when you label the crack. Of course, we made also a review by expert process. So at the end of the labeling, there were some experts, let me say senior experts that have more understanding of the phenomenon, that reviewed some samples of the data set. And when something goes wrong, for example, I saw that all the images labeled by Giovanni Giacco, 50% of the images labeled were wrong. We dropped all the label and we started with the labeling again, because of course for us the quality of the data set was very important. As you can see, an important aspect is that we have very highly heterogeneous images. We have, unfortunately, images from very far from the buildings, other that are near to the buildings. There are several conditions of brightness, shot angles, backgrounds, etc. So it's a very complex task. For our approach, we tried to not force the scene to be in a specific way. For example, just in the front with the right brightness. We try to do that because, of course, when you collect images from smartphones or from drones, you can't be sure of what you have in your system. So we try to train a system that was more robust about that. Here there are some analytics about data set. In any case, we have more or less now 9,000 acquisition of several parts of several aspects of the buildings and the cracks in our data sets. I won't go into the details of this, but let's go on. I don't know how many of you here know about deep learning and convolutional neural networks. I did not prepare a slide about that, so I just give to you some points about that. If you have questions, feel free to ask to me at the end or by mails. The idea here was to not create let me say, a deep learning model from scratch, but use what was the state of the art at the moment for image classification and semantic segmentation. And at the moment, maybe already you know, but the state of the art, at least 2 years ago, was about convolutional neural networks. So we just used a state-of-the-art convolutional neural networks that was the ResNet. We tried, of course, with several one, also with one provided by us, but at the end we used a ResNet convolutional neural networks. And let me say, we have two different kind of approach, because for the segmentation of of opening, we need to have a semantic segmentation. And in the first version of the crack detection, we made the patch classification. So what we did is put in our model a 224 for 224 patches pixel images, and say for this patch, if inside this patch there is a crack and the severity of this crack. So at the beginning, we did not start with the semantic segmentation of the crack, but with a patch classification. So we say that in this patch there is a part of a crack, in this patch there is a part of a crack, etc. This was the first approach that we used at the beginning. But the idea, why we started with that? We started with that because at the beginning the data set we had was not so big, and if you need to make semantic segmentation, so you need to create a mask where you tell, okay, this pixel is cracked, this pixel is not cracked. You need to have a more you need to have a bigger data set. So at the beginning we started with a patch-based classification. Okay, this is just to give to you the model that we used for the segmentation, but I will go on. Is just a normal UNet network for the semantic segmentation, where we changed the backbone, the encoder part of the UNet with a ResNet network. This is very common in the literature as a semantic segmentation deep learning model. Is a very common model. Those are the results that we had. They are pretty good on the data set that we use. As you say, we have an accuracy that is better with the ResNet 34 and not with the ResNet 50. But when we collected this first result, the problem is also with the data set. This was not so big. So the ResNet 50 that has a lot of more parameters, because you have more or less double of the ResNet 34, was not so able to train. But in the second version, we saw that the ResNet 50 outperformed the 34 model. As you see, those are the metrics confusion. The results are pretty good, because more or less they are everything is greater than 90% of accuracy. And just to show to you a little example, of some wrong prediction that we had. For example, here in the B image, this is a false positive, but this is a wrong false positive, because the patch was labeled in the dataset as no crack, because the user did not view the crack inside the buildings, but the model did. The model did because, so this is a very important aspect, because this means that our model tried to generalize better than the quality of the dataset in itself. Of course, we have problems, because, for example, in the image A, here the image is not at high quality, and this is not a crack. This is an electric lines on the surface of the buildings, and here our model detected it as a crack. Of course, this is a false positive. But anyway, this is just the result of the first experiment. So of the first version. So this is the end of our solution. The end of the is an example of the output of our proposed approach. So you have the localization of the openings in the buildings, okay? So you can define where the cracks, you collect the cracks with their severity. As I said to you, is a patch-based classification. And you define the severity, low, moderate, high. So you can compute the damage assessment matrix, and you can also in the piles, in the spandrels, in the rigid zones, and of course technicians know what means piles, spandrels, and rigid zones. That are several parts of the structure of the masonry buildings. They can see the matrix and tell, okay, they of course they can compile this form, and also they can have a judgment of at the beginning of the wool damage of the buildings. Of course, you need to make this assessment for all the buildings of the for all the facades of the buildings. Okay. So what is the problem? What is the problem of this solution? I don't know. Maybe someone can guess about it. I can answer for you, but what is the problem of this solution? The problem is that with the patch classification, you don't know what is inside this patch classification. Let me say, I can define that is this crack is as a severity that is higher than this, and we made this with a good accuracy. But how long is the crack? How big is the area? Because let me say, if we have here we have just a small part of the crack, and for me it's crack the wool box. And also here, but here, for example, the crack is more in the majority of the patch. So we need to have a definition of that. We need to characterize better the cracks. So we started to improve our first version of the solution with a second version of the solution. What was the solution and the proposed approach? We tried to improve our solution applying a semantic segmentation approach. So we did not apply the patch-based classification, but we tried to segment, create a mask of the crack on the buildings. The output is here on the right. So we could characterize the cracks not just by the number 2, 10, 7, but also about their length, their thickness, and their area. Okay. This was possible because we made a boost of our data set. So we collected other images, we enlarged our images, because of course to train a semantic segmentation algorithm, you need more and more images. And what we did was producing this is, I think, yes, this is the buildings, the initial buildings that we fed in our model. This is the output that we have. I cropped the left part of the image, but this is just this part because I did not have space in the slide. But this is the mask that our model fit, the output of our model. As you see, you can have all the cracks inside buildings, and this is of course more precise because you know the area, as I said, the area, the length and thickness. Of course, we need to make some morphological operation, some very common computer vision morphological operation to post-process our data. So, for example, we made some closing morphological operation, skeletonize, if someone of you know. Why? Because of course, with the first mark, with the output, you can know and you can compute the area. you can compute the area of the cracks. But if you want to know the length, how you can compute the length of the cracks inside on a surface? So we made this operation to pass from our mask on the left to the line, single line. These are lines of the cracks. And we made this just without artificial intelligence, just with the morphological operation. So we have single lines, and with this, it's very simple to characterize the length, because you can just count the pixels and have a length of the length of the crack. It's worth to note that when I'm talking about lengths, it's not about absolute lengths. This is a problem because we don't know the resolution of the image. So we can say that, okay, from ear to ear is 20 pixels, that corresponds to 20 centimeters. We can't do that. So we developed a methodology that works just with relative lengths. So we just talked about 20% of the area, 20% of the scene in length, because we can't go in an absolute way, with the absolute measures. And this is, of course, a problem, but a challenge of our approach. What we did was using these. We now know three things: that is the severity, the area, and the length. And we created with this approach we give a judgment that is based on the MS 98 grade, that is an European scale to assess the damage of earthquakes. And so this is just an output of the approach. This is the label that was made by a human. This is the output of our model. This is the computation made on the percentage of pixels, the length, etc., made on the human-made classification and on the human-made and on the artificial intelligence made classification. And this is the score that we have. As you see, we have D2 and D2 for all the both the approaches, both the manual and the automatic one. Of course, you can see that there are some difference, because you have some difference in the percentage, but they are very similar. So at the end, the damage, the final damage assessment is the same. This is just another. This is the example from the image that we saw before, and yeah. So the idea is, we are at the end. The idea here is that starting from image, you can have the damage, the classification of the damage at the end from grade 1 to grade 5, and you can have this for all the buildings or the image that you put in the system. And of course, this is everything automatic. You just need to have images of the buildings, and everything is after that automatic. And just to give to you what will be the future of our solution, we are trying to understand how we can integrate this kind of process in a BIM application. So in how we can, starting for example, from a BIM created from by drones images, how I can apply our model to the BIM model, and we can put on top of the BIM model our result. And of course, this could be very useful in the future when you need to make a lot of plans, because of course, if you can integrate all this data in a BIM models and in a dashboard, when you can have an overview of the data, you can make decision in a faster way. So this is something that we are working on. We are developing the products thanks to the first approach that we developed. We are just at the beginning. At the moment, we have just the products that put in input all the facades of buildings and put in output the damage. this is something that we are starting to work. But I think 2-3 months ago we started to understand how we can integrate the whole approach in the tools that everyday technicians use to manage this kind of disasters. So I think I'm at the end. Okay, I don't know if you have a question or I'm happy to answer to you. Okay, I think there are no questions.
I think there are no questions as well.
Okay. Okay. So
Thank you very much,
thank you very
Giovanni.
much. Thank you very
Good
much
to have you.
for your attention.
Okay, everybody. Let's have a break. The next meeting will be at 2 p.m. Eastern European Time by Antonio